Okay, our final talk before lunch is by Adrian, who'll speak about Stein's method from Esseen to Stein. Go ahead.
Thank you very much. Apologies for not being there in person. We'll be arriving tomorrow morning, so the subsequent two talks I should be able to give them at ICTS in person. So this is sort of a prelude to Stein's method I want to give you to sort of move towards a full Stein method in the subsequent two talks. So let's start with Esseen. Carl Gustav Esseen was a Swedish probabilist who is famous for what's called Bayesian theorem, which is a rate of convergence for sums of independent random variables, which was a breakthrough in the 40s. While the convergence itself was proved much earlier, the quantification of that result took much longer. So let me here have this snapshot from Esseen's paper so that we have the setup. So let's assume we have n random variables. Let's assume the simplest case, IID, x1 to xn. They have a common CDF, a cumulative distribution function, and we denote by little f the characteristic function. Here, the definition of the characteristic function should be familiar to all of us. We assume, to simplify things again, that the mean is 0, and we assume that the variance is given by sigma square. We further assume that the characteristic function has this expansion. The expansion is about 1, and that's the expansion. As you can see, that's just a Taylor expansion about 0. Sorry, it's not about 1, it's about 0, and it decomposes into moments. So the 0th moment is just 1. The first moment is 0 by assumption, and the second moment here comes out with sigma square, and then we have an assumption on the third moment, or rather higher moments, in this case, variance plus a little bit, or if you want to go to third moments, this would be the case alpha equals a half. So then the main result says that the cumulative distribution function of the standardized sum of these independent random variables compared against that of the standard normal is bounded by 1 over n to the alpha. The case we're interested in usually third moments, in which case alpha is a half. So that will be 1 over square root of n, which turns out to be best possible. Similar results were known before, but with log terms in them. So this is the first result, which is optimal. So the key to obtaining results of this form is the inversion formula. So we can go from distributions to characteristic functions, and we can go back using the inversion formula. So we have here the difference of two CDFs can be expressed in terms of the differences of their characteristic functions, an integral over that. Now I put the quotation marks because there's always issues with convergence of this integral. And that's in some sense is what Esseen was successful in circumventing. So here is in some sense the technical breakthrough that allowed Esseen to do that, which is a truncation formula that says we don't have to integrate from minus infinity to infinity. All we need to do is to integrate from minus capital T to plus capital T, call that epsilon. And then we can bound the distribution function, the difference of two distribution functions by this epsilon. But of course, there's a price we have to pay, which is of the form order 1 over t. So there's the trade-off here. The larger we make t, the smaller this truncation error becomes, but then also the bigger this epsilon becomes. But this is sort of the technical breakthrough that Esseen managed to do in the 1940s. So let's see how he argued roughly. How do you show this? I mean, we still have to calculate this integral, or at least upper bound this integral. And what Esseen did is essentially the following argument. So we have the characteristic function f is 1 minus 1/2 sigma squared t squared plus error term from the Taylor expansion. And we pretty much argue directly. So let's say the standardized sum has a characteristic function. We call that f sub n. Because they're independent. Characteristic functions factorize if we have sums of independent random variables. the corresponding characteristic functions factorized. So we have the original characteristic function to the power of n, and inside here we have some scaling. We want to divide by sigma, and we want to divide by square root of n, so that we have a sum of random variables with mean 0 and variance 1. So you just replace this approximation. It's just a Taylor approximation here, error. And so we just plug that in, and you can see the sigma square here cancels. Then the n, square root of n, goes to the denominator, and what you recognize that this is just the exponential formula that tells you that in the limit this is e to the t minus t squared over 2, which is the characteristic function of the standard normal distribution. Now enters Charles Stein, a statistician in Stanford in the 60s, and he wanted to prove a central limit theorem for what's called a Höfting statistic. I don't want to go into the details of that, but for his lecture that he was presenting, he wanted to have a different proof than the one using characteristic functions. And this is the following observation that he made. If you write down the characteristic function of the standard normal, let's call that little g, that's e to the minus t squared over 2. Now he noticed that this function satisfies an ordinary differential equation. Of course, it's one of the simplest ODEs that we can write down. Okay, so that's g prime, g prime of t. So that's the t here comes out. We get the t here, and then of course we have the minus here, which corresponds to the minus here. We have the boundary condition that at 0 we need this function to be 1 because it's a characteristic function. So his approach was that, well, if we can show that our characteristic function of interest f sub n satisfies the limit, we should hope that we can prove that way that fn or this variable of interest converges to the standard normal. Rather than doing the calculation directly, which is what we've done here, maybe we can also use this kind of ODE idea to do the same, or to get the same result in a different way. So again, here, let's write down what this ODE is. This is sort of an analytic expression, g prime equals minus t gt. We can write back what it means in terms of random variables. So g prime is just the iz here comes out of the exponent, and minus t gt is just this expression. So that we are back to random variables rather than analytic functions. Okay, so let's write this out again, what we have here. So that's g prime, and that's minus t gt. And what he noticed is that, well, we can rewrite this, and we can sort of hide the exponential function, this complex exponential function. So he noticed that you can write phi sub t, define this function as I times e to the itz. And you notice that the left-hand side here can be written as z phi tz. Okay, you can recognize I e to the itz. That's just this function here, and we have the z left over. On the right-hand side, this minus t e to the itz can be written as phi prime. If you take the derivative with respect to z here, we get an I t out, so the I square will give you the minus sign, and the t will come out. Okay, that's just rewriting this, but now we work with random variables sort of directly rather than having to work with functions. Okay, so again here, we have this, that's the basic idea. If our characteristic function satisfies this ordinary differential equation for all t, and of course we have the boundary condition that at 0 we need this to be 1, that's equivalent to saying that these two expectations are the same for all functions of this form. Okay, so far so good. Now Stein, and that's one of the key insights, was that, well, there's nothing special about this phi here. This identity actually holds for all phi. Of course, they have to be differentiable. They need some tail conditions that these expectations are well defined, but pretty for general all phi, this is equal. And not only that, it is actually if and only if. So if z has a standard Gaussian distribution, then this is if and only if this identity is true for all f with some conditions. And that's what sometimes we call that Stein's lemma. Now let's prove this. This is just integration by parts, essentially. There's nothing mysterious about this, but I want to go through the calculation that you really see that this works in general. So we have expectation of phi prime z. We just write out what that is. So we integrate phi prime against the normal density, and then we integration by parts. So we get rid of this derivative here, and you can see this z coming out here, and the two minus signs will cancel. We get this integral, and we get expectation of z phi c. So this is really general. Now, the reverse direction is a bit more technical because you have to choose your phi in the correct way, and then you have to argue that for a certain family of phi, this is enough to prove that the density against which you integrate indeed is the standard Gaussian density. So here we have now various characterizations of when a random variable z is standard Gaussian, if the characteristic function has this is exactly of this form, or if this ODE is satisfied for the characteristic function, or if we have this identity for all phi, for a large family of functions phi. And then we deduce the principle that if a random variable Wn of interest is close to Gaussian, well, these identities should be holding approximately. Now, moving forward, I will drop the index n, because ultimately Stein's method is about finite sample bounds. So we don't need to let n go to infinity. We will get finite bounds eventually that hold for finite n for whatever parameters you have. So we can drop the n and just work with a random variable. And traditionally in Stein's method, we call the random variable of interest is w, and the target random variable here, the Gaussian random variable, is called denoted by z. So these are sort of standard variable names that we use in Stein's method. Now, what I've haven't discussed so far is, well, that's a nice idea, but how do we actually get an approximate ordinary differential equation of this form? How do we get something like this? And that's what we'll be talking about today. Next lecture, the second and third lecture will be more about how do we get expressions of this form. But for today, we will not do the full Stein method case. We will try to get something of this form to show you that you can get approximate ODEs for the characteristic function. And you can actually use that then to get quantitative bounds. The key here is auxiliary randomization. That's what Charles Stein called it. And that's the key idea to all or most of Stein's method. So, as I've noted, the key was integration by parts. That's the key tool we've used for the Gaussian distribution to show that this equals, that this identity is true. But in general, if I give you a W need not have a density at all. It could be integer valued, and in which case you do not have an integration by parts formula. Moreover, most of the times we don't know enough about W in the first place to even think about an integration by parts formula. So what Charles Stein instead did is he said, well, let's replace differentiation by differences, okay? So that we work with differences to replace differentiation. So the key idea is that we take our W and we create a small perturbation of W. We call that W prime traditionally. And then we try to work with that and hope that we can get sort of approximate integration by parts formula or calculations that are in the spirit of integration by parts to derive these kind of identities. So that's one of the first key insights of Stein, is to say, let's work with small perturbation, auxiliary randomization, to extract information out of W. So let's have an example. What would such a perturbation look like? I'll give you again, x1 to xn, a sequence of random variables, finite here. We don't need infinite. We we fix n. They are, for simplicity, IID, mean 0, variance 1. And we're interested in this W, and we standardize it by 1 over square root of n, so that we have expectation 0 and variance 1. I call this bold X to indicate that this is the whole family. So later we will do some conditional expectations, and will condition on this whole, assuming we know all these individual values. So what does such a perturbation look like? What Charles Stein did, he said, okay, let's just pick one of these summons, throw it away, and replace it by a new copy of that. So capital J here is a random, uniformly chosen random index. You remove that summoned out of the sum and replace it by a new copy. We call that X prime. Okay, that's certainly a small perturbation because you haven't changed the whole sum, you've just changed a small part of it. Now, here's an interesting observation. This gives you what's called an exchangeable pair. Exchangeable pair means that the distribution of W and W prime is exactly the same as W prime and W. And the reason is that if I'm giving you W and W prime, you can see that they're different. Or if I even give you this whole family, and then the new family will be in one of the positions. I've changed one of the x's and replaced it by an x prime. I can give you the both families. You can tell there is a difference at position J, but you won't be able to tell which one was the original one, which one is the new one. It could have gone the other way around. So you can't tell from what I'm giving you which is the original, which is the new one. And that makes the construction exchangeable. Great. So now we have a random perturbation of our W. And let's do some calculations. Let's do some basic calculations related to the difference of W prime and W, because ultimately, as I said, we want to do differential calculus, but instead work with differences. So ultimately, W prime minus W will give us sort of a lot of information about what's going about W ultimately. So let's just calculate the conditional expectation of W prime minus W given X. You can condition on W, or you can condition on X. As Will says, in this case, it would be enough to condition on W, but the calculation is more transparent if I'm conditioning on the whole sequence X, of the original sequence X. So the difference is just the new one, the new random variable minus the old one, given X. Now, X prime is independent of X, so that expectation is just 0. Okay, and the old one that's measurable with respect to X, all I need to do is I need to average over J. J is still random, independent of X. I have to average over that. That'll give me a sum. 1 over n here is just the probability of picking each specific index. So that's the quantity that we get. And you can see we get back to W. Okay, because that's just the original sum here that you can identify with this prefactor minus 1 over n. And let's hide this a little bit and just say call that lambda. Okay, makes the optics a bit better later on. Okay, so interesting observation. The difference condition on X turns out to be linear in W. So you might have well conditioned on W here. It would have be the same at the end, because this is at the end, you can see W comes out. Okay, let's look at the squared version of that. We can do a similar calculation. Maybe in the interest of time, I don't want to go through it, but what you can see here, you get sum of 1 plus x I squared over 2n, and that is not a function of W here. You cannot just replace x by W here. This is a function of x. But if you think about this, 1 over 2n, the sum of that is just a half, and xi squared over 2n, and the sum over that by the law of large numbers converges to 1 as well. So you get a half, roughly a half plus a half, which is 1. So you get very close to the variance of W. So this sum here, this conditional expectation, is close to the variance of W, which is 1 in this case. So we have these two ingredients. So let's try to derive an ordering differential equation for the characteristic function f, which is the characteristic function of W. So I've suppressed the index n here. So let's just plug in what it is. That's this expression here. So this is true for any exchangeable pair that satisfies these two conditions. So we're not specific to the previous construction. So that's just, we will be using these two properties here only. So that's the derivative of the characteristic function. You see the IW came out here. Now, first thing we do is we take this expression, the W here, and replace it by the difference. We can do that because here there's a W, and so we can condition on W, replace this W here by this difference. And of course, I have to add this constant lambda in here to make it equal. Now, the following calculation is sort of, they're easy, they're straightforward, but why Charles Stein came up with them, that is opaque, that is not clear, and to this day it is unclear to me. I mean, he has some, in the 80s, he wrote a book about ways of doing these things, but it's sort of unclear. But maybe you just play around with these expressions for long enough and you get what you want. So first thing I do is I split this expectation in half. So just double it up, divide by 2. Okay, it's the same. But what I'm doing now, I use exchangeability. I replace W prime by W. I replace W by W prime, and I replace W by W prime here. So I haven't done, because it's exchangeable. The expectation is the same. Now what I do now, the second part remains as it is. But now I absorb this minus sign into this difference, and I swap the two. So, and what I end up with is the same prefactors here. You can see W prime minus W, but now here the E to the ITW prime and here to the ITW has changed. Okay. So I'll combine, I'll get this. I extract a factor E to the ITW. Let's do that. I to ITW, and we get in here this expression, and which is nice here because you can see we get back W prime minus W. So we work with differences of functions. So as you can see, well, if W prime and minus W, if W prime is a small perturbation of W, this is going to be close to 0 in probability or in L1 or in L2, but this is going to be close to 0. That means this expression is going to be close to 1. So we can use Taylor expansion to approximate this by W prime minus W. That's this wiggle here. That's Taylor expansion. And so we end up with this expression here. Okay, so we have the W prime minus W here, and we get another one from here. That's that. So now you recognize this expression. Let me quickly go back. That was the second calculation. Well, this is close to 1, not just in expectation, but actually in probability. So that's this expectation here. The T factor came out from this Taylor expansion. You get the T here. And you get an I here, which combines with the I here to get the minus. Okay? And so what you get is approximately minus T to the F of T. And there we are. So this is how we've derived an approximate ordinary differential equation for the characteristic function using this idea of auxiliary randomization. If you want to identify where's the integration by parts in here, I don't really know. What I know is that these calculations give this sort of approximate ODE. I would have to think about carefully where exactly is it that we can find this really integration by parts formula in here.
And Adrian,
what matters here,
you do not use the form of W, you did not use, right? You just use the fact that the mean of W prime minus W was of that form, right?
Yes. So the only thing we've really used is this. That's exactly. Right.
So that only the red part as well, not the black part in the middle as well.
That's right. That's right. So and that indeed is in some sense, you want to write down an abstract theorem. You say, okay, give me an exchangeable pair that satisfies this identity. You show me, or you can show that the expectation of this squared expression equals the variance of W. And if it in fact is close to W when you condition on W, so this conditional expectation is close to the variance of W. So the expectation is exactly W, the variance of W. And if this expression here, which is a random quantity, is also close to the variance in probability or whatever where you measure that, you can then actually prove a quantitative result and measure how close this is to the Gaussian distribution. I'll give you an example. So that's what this is sort of not what Stein originally did, but that's what a few years later a Russian mathematician called Tikhomirov did. He sort of said, okay, let's go back and use characteristic Stein's idea of auxiliary randomization, plug it into the characteristic function machinery, and then see what quantitative bounds you can get, and can show that we can also extract quantitative bounds. Again, that's not what Stein did. I will tell about what Stein exactly did in the next lecture. And so I sort of picked up on that work again a few years ago, because it turns out there's something that's puzzling, because if you work with characteristic functions, there's a technical phenomenon, which is that when you use characteristic functions, it doesn't matter whether these x's, these summands are bounded or unbounded. Whereas if you use Stein's method, there's a stark contrast between the bounded case and the unbounded case. The bounded case being usually quite straightforward, and the unbounded case being usually quite painful. And so that's why I was interested in going back to this Tikhomirov's idea of using characteristic functions and this part of Stein's method to get some normal approximations for triangles in Ereshefsky random graphs. But here is sort of the result. This, you have an approximate ODE. By approximate, I mean we don't know exactly what these factors A and B are. You can give some upper bounds. In the previous case, when you have this exchangeable pair, you can upper bound the factor A by the third difference, expected third difference, and the B can be upper bound by this quantity. You can see here, I didn't do the Taylor expansion inside here. There's always technical issues that you have to worry about, and it unfortunately doesn't come out as clean as in this calculation here, where you have just the variance of this conditional expectation. But this in spirit, it's the same, right? This is essentially W prime minus W here. So you have indeed the conditional expectation of this squared, but the variance of the conditional expectation of the squared difference in spirit at least. Okay, so that's sort of the prelude to Stein's method. And if you want to have some references, the sort of two standard references nowadays is a survey paper by Nathan Ross called Fundamentals of Stein's Method, which is sort of a nice short introduction in most of the standard techniques and results. Among one of them is the exchangeable pairs approach that I just spoke about, and an actual abstract theorem that I can say, okay, you have your exchangeable pair, plug it in, and then you only need to do moment bounding. Let me quickly go back to give you the beauty of that, because all you need to do, you see the right-hand side, once you give me an exchangeable pair that satisfies this linearity condition, all you need to do is calculate these quantities. So that's a moment bounding exercise. Of course, in this case, if you do this with characteristic functions, you end up with these kind of less nice quantities that involve the complex exponential function. If you do the actual Stein's method, these will become much cleaner. There's of course also a book by now a standard book by Louis Chandler, Golsin, and Qimon Xiao called Normal Approximation by Stein's Method. And the theorem I just told you about, this apologies, this theorem that deals with this is a paper that I wrote a few years ago in to get Kolmogorov bounds for triangles. And again, the issue was that the number of triangles or certain this exchangeable pair when you work with triangles is unbounded, or can become unbounded as n goes to infinity, and that causes the technical issues when you use Stein's method. Whereas if you use characteristic functions, it sort of disappears at the cost of having to deal with this more nasty expression. Okay, so next time I will talk in more detail about the actual Stein method itself. Thank you.
Any questions for Adrian?